Hi, I want to show you how to solve a particular type of problem that pops up a lot in Physics 202 and also in Physics 201, and maybe on the MCATs and things like that. So I'm going to use an example from an exam that we had recently that was about capacitors. And this type of problem that I want to talk about is where they say we want something to change in, let's say, the energy that's stored of this capacitor, or in the resistance of this wire, or in the potential energy of this system. And they say that one parameter might change by a certain amount, and they want you to figure out how the other thing changes. So this is what I would call the before and after type of problem. So let me illustrate with a specific example here. So they give you a capacitor. They say it's got circular plates, which I've drawn here, and they're connected by some particular potential V. And it has a diameter. Each plate is the same. They're circular. It has a diameter of capital D and a distance between the two plates of little d. They say that this stores a certain amount of potential energy, electrical potential energy. We'll call it U. And what they want to do is create a new type of capacitor that will store 3 times the energy. So the energy stored will increase by a factor of 3. Now what they say is that they're going to store it basically with the same potential. So the same battery will be across these plates and the same distance between the plates. But what will change is D, the diameter of these circular plates. And we're going to assume that if you're going to store more energy, you probably need a larger diameter. Okay, so we'll call that D prime. So you want to go from D to D prime, and you're told that the energy goes from U to 3U. And the question is, what's going to be D prime now? How much bigger do you have to make the diameter in order to get 3 times the energy? So this is the type of problem that you have. You have to compare something before and after. The real handle on the problem is you have to figure out some sort of equation or expression that allows you to talk about the potential energy in terms of the diameter of the plates, okay? So now you can't look on your formula sheet immediately and see, oh, here's the potential energy of a capacitor in terms of the diameter of the plates. So you're going to have to use more than one formula. So let's take a look at this. So here's the before and after. So what you have to do is start looking at formulas for the potential energy. So down here, we've got a formula for the potential energy. It involves the capacitance. It involves the capacitance. And what you hopefully will remember is that the capacitance can also be expressed in terms of the geometry of the plates. Okay, so if you look at this formula here, the potential energy will change. I can make it increase to U prime if I change the capacitance. Remember, they told us that the voltage would be the same in both cases. Here's the voltage there, and here's the voltage there. They're going to be exactly the same. So the only thing you can change here is somehow the capacitance. And you can't change the distance between the plates, but you can change the diameter. So we want the capacitance to go from C to 3C. And if that happens, then U will go to U prime, where U prime is going to be 3 times bigger, because I've just inserted a factor here. So if we can increase the capacitance by a factor of 3, we can increase the energy stored by a factor of 3. All right? And that's illustrated by this. So the capacitance has got to go to 3 times its value. And then you have to look for a formula that talks about the geometry of the plates. So here capacitance is given in terms of the area, A, times epsilon naught, the constant, the permittivity of free space, divided by the distance between the plates. And so if I want the capacitance to increase by a factor of 3, then the geometry's got to change somehow. So C prime has got to be 3 times bigger. Well, I can't change D, the distance between the plates. That's got to be the same, we're told. But what we can do is we can make the area 3 times bigger. So the area's got to get 3 times bigger if I'm going to pull this off. And so that means that C prime divided by C has got to equal a factor of 3. Here's the C prime. This is the new capacitance we're going to. It's 3 times the original value of C. And we know from this previous formula that's going to give us 3 times the potential energy. Okay, so we're off to the races in a sense. Now what we're going to do is we're going to fit in the diameter into this area expression here. So the area, if it's a circular plate, is going to be pi r squared. Now in terms of diameter, when you divide the diameter by 2, that's the radius. Okay, so this is pi r squared. This right here is in the area of the first capacitor plate. This will be the area of the new capacitor plate. Notice it's got D prime. That's the thing that we're looking for, is the new diameter. All these other things are the same. epsilon naught is going to be the same. The distance between the plates is going to be the same. So if C prime is supposed to be 3 times bigger than C in order to have 3 times the potential energy, I can make a ratio. I can say C prime over C is going to be 3 over 1. And now I can put the geometric expression for the capacitance of the new capacitor up here, and I can put the geometric expression for the capacitance of the first capacitor down here. The only thing that's different is I've got D prime up here. Okay? So that's the new diameter. So when I divide one thing like this by another thing like this, I can cancel things that are above and below this fraction line. And that's what I'm showing right here. Pi appears in both equations. Epsilon naught appears in both equations. The distance between the plates appears in both equations. And then this 2 is going to appear in both equations. So when I cancel all that, what I'm left with is something like this. So C prime over C is 3 over 1, as we've said. And the only thing that didn't cancel is D prime, quantity squared, over D, quantity squared. A little cross multiplying. So D squared times 3 is going to equal 1 times D prime squared. So now I have this equation, 3D squared equals D prime squared. Remember, my goal is to get D prime. And what I have to do is solve for that. So I take the square root of both sides. And when I do that, I get D prime by itself, no longer squared. I get D, no longer squared. And then the 3 turns into a square root of 3. So what that means is that D prime has got to be square root of 3 times D. So it's a little bit bigger by a certain factor. It didn't triple or anything like that, but it got bigger by a certain amount. And D, if it goes to now square root 3 times D, that will allow the potential energy stored in that capacitor to become 3 times larger. So just to summarize, what I would say is represent the before and the after, find the variable that you're interested in, and that's the prime, and then look for equations that can somehow constrain how that variable is going to be different. If you know that the potential energy is going to triple, then you can get a handle on the diameter if you know something about how the capacitance is going to be related to the diameter. It's going to be related to the diameter through the area here. So I admit there are lots of little steps in here. This is a tricky example. I purposely picked it, so hopefully that will help you a little bit. But yeah, problems like this pop up a lot in physics where they ask you to compare one thing to another after they change a certain parameter by a factor of 2 and another one they cut in half, things like that. So here's an illustrative example of how to do that. I hope it's helpful.